Hi, welcome to the first exercise session with Jupyter Notebooks. So the idea of these exercise sessions is that we are going to run calculations with a numerical library that is called Picula, and this will effectively allow us to compute different Hamiltonians, understand electronic structures, and even include interactions, all just with a computational package without actually having to do any analytic calculations. And so we are going to start with the first session that is focused on second quantization mean field and spontaneous symmetry breaking. And the contents of this exercise session are very much what was discussed in the recording of the lecture. As practicality, let me just remind you that there will be two different types of exercises in this Jupyter notebook. There are the core exercises, that these are the exercises that are the most basic, and that it's very good that you understand this in every single notebook. And then there are the other exercises which are more elaborate and more advanced, that are the challenge exercises. And these ones you don't need to understand all of them, but it can be a very good and motivating exercise to try if you want to do something more advanced. Okay, and so the way in which the exercises are organized is that you have a template code, and this template code computes some basic thing that we would like to consider. For example, in this case, so just the spectra of a timer, and the result of the code is printed usually as a plot, and then afterwards, this example, you have a few questions that you need to answer. And so let's start with this code. So this example deals with the electronic structure just of a timer, so two sides connected by a hopping. And so the way this is built is one takes a chain with two sides, makes a zero-dimensional version of it so that you only have two sides remaining per unit cell, and then you get the Hamiltonian of those two sides, and then from the Hamiltonian you get the electronic structure, and you plot the electronic structure. And so what we see in this plot is that there are effectively four eigenvalues. This is because we have two sides times 2 from this spin degree of freedom. And so these two states are the bonding states. These ones are the anti-bonding states, and we have two because we have spin up and spin down. So let's go out with the first question. So there are two sites in the system. So why do we have four eigenstates? Well, that's effectively what we discussed before. And why are the states degenerating energy? Well, the reason why they are degenerating energy is because spin up and spin down, they have the very same energy. So in case we wanted to break the degeneracy between these two states, what we could do is simply to add a term that breaks the degeneracy between the spin up and spin down. So this is without the term, but now we can add, for example, a magnetic field to the system, like a Zeeman field in this way. And when we do this, you see that the breaking of the degeneracy between spin up and spin down happens. Okay, let's move on to the next exercise. So now we are going to deal with a finite size chain. This is a chain that has either one side or two sides or three sides or four sides, and this is effectively controlled by the value of L. So L goes from 2 to 60 in steps of 2. And so what we are doing here is we are going to create a chain that has L sides. We compute the Hamiltonian of it, we compute the eigenstates, and then we plot the eigenstates. So here on the left, we are effectively just plotting the chain of the length, just to have it as a reference. And here on the right, we are plotting the eigenstates of the system. So the bigger the chain, the more and more eigenstates we have. And so now let us go to the question. So the first question is, why does the number of eigenvalues increase with the system size? The answer to this question is that, well, as we make the system bigger and bigger and bigger, the tie-binding matrix that describes this system becomes also bigger and bigger and bigger. And the bigger the tie-binding matrix, the more eigenvalues it has. And in particular, it has as many eigenvalues as the dimensionality of the matrix. So if we have a matrix that is 50 by 50, we will have 50 eigenvalues. If we have 200 times 200, we will have 200 eigenvalues. And now the next question is to make a log plot of the gap and obtain its functional dependence with the system size. Okay, so to do this, we can do the following. So the gap is effectively the energy difference between the positive energy and the negative energy. And so what we can do now is we can say, okay, so let us define the gap as the energy difference between the smallest positive energy and the smallest negative energy, and the biggest negative energy. So this is the definition of our gap. Okay. And now we are going to just create an empty list where we are going to store all these gaps. So now we compute this and we can just plot our gap. So what we can do now is make a scatter plot of our gaps. First like this, and you see that, well, we have a gap that becomes smaller and smaller and smaller. So for small system sizes, the gap is big. And then as we make the uh, gap, the system size bigger and bigger, then the gap becomes smaller. It can be interesting to plot this as a log plot. And the idea is that when we plot it as a log plot, we can actually extract what is the power that the gap versus L has. So we are going to make just two plots as a reference. So the first one is going to be the same as the one that did before, and now we are going to do another one, which is a log plot. And now that we plot it as a log plot, we see that in the log of distance versus log of length versus log of gap, we get a perfect line. And if you look at the slope of this line, you will see that the slope is effectively 1. So from 3 to 4, from -2 to 1, we effectively have a slope 1. And so what this means is that the dependence of the gap as a function of the length is 1 over L. And this is actually what we expect from particles that have a linear dependence between momentum and energy. And this is what happens at half filling. Okay, so now let us move on to the next case, which is the density of states of a finite system as a function of the system size. This is, of course, a slightly more complicated problem, and let us go through it. So first we can look at the plot. So in the plot, what we have here is first the eigenvalues of the system as a function of the system size. This is very much as one of the plots before, and here we have the density of states. The density of states is just a quantity that tells us how many states do we have in a certain energy window. What this means in practice is that every time that we have a state at a certain energy, then the density of states is going to become non-zero. So you see that the plot on the left and the plot on the right, they are effectively very similar. It is just that the plot on the right has a little bit more contrast because it tells you in which places you have more eigenvalues than in others. And so let's look at the code, how it works. So the idea is that we are looping over different lengths of the system, and we create a system, we make it of a certain length, we create a Hamiltonian, and then we can optionally add a modulation to the on-site energies of this system, which is something that we are going to do afterwards. We compute the eigenvalues, we compute the density of states, and then we can plot the eigenvalues and store the density of states. So let us go to the question. So make the system even bigger. What happens with the density of states? So making the system bigger means that we just go to bigger lengths. And so what we can do is just to increase the length here. So from 60, we can go to 100, for example, and run it. And you see that when you go to 100, effectively you get a continuum of the state. So instead of having just very specific branches in the density of states, you get a continuum. And this is the limit in which we usually work in solids. States are no longer a discrete set, but they are a continuum set. And so that's why the density of states is a useful function to know when studying the electronic structure of materials. And now the next question is to add a finite modulated on-site energy V and see what happens to the spectra of the chain. This effectively breaks the original translational symmetry that the chain has. And this is something that we can do just by looking at this function over here, that is a perturbation that we add. And so effectively by default, there's no perturbation, so the value is 0. And we put a finite value. What's going to happen is that we are going to add an on-site energy that depends on the position of the site, and it follows a cosine-like form. And in general, this is going to be incommensurate with the lattice. So we can start with a small perturbation like 0.5 and see how this looks like. So with 0.5, you see that we have a gap opening up at finite energies, and that this gives rise to an electronic structure that it's a little bit more complicated than the one before. If we make the strength of the perturbation even bigger, you see that the gap is going to even become stronger. So the stronger the perturbation, the stronger the gap that appears. And if we change the modulation of the perturbation, also the gaps are going to change. So if we replace square root of 2 by square root of 7, you see that the gaps are different. And if we do, let's say, something slightly different, you see that we may even have more gaps. So instead of having just 2 gaps, we may even have 5 gaps. And we can even reach a regime where we have, let's say, many gaps. Okay, so what we learn from here is that we can start with a system that has a continuum density of states, and when we add perturbations to it, we get a density of states that is very different, in particular that opens up gaps. Okay, let us move on. So now we are going to look at how we can get magnetic order from electronic interactions, and in particular from interactions that we treat at the mean field level. And so the idea is the following. We are now going to work with a one-dimensional chain, also for simplicity, that has a certain interaction. And the way we include this interaction is through a mean field Hamiltonian. So this is effectively what you watched in the recording. We have a density-density interaction. We do a mean field decoupling. And with this mean field decoupling, we solve self-consistently a set of mean field equations. And once we solve the mean field equations, we effectively get an effective single particle Hamiltonian that includes interactions through additional terms that are interaction driven. And so in this case, we are going to start first with a ferromagnetic guess for the mean field equation. So we solve the mean field Hamiltonian with a certain interaction in a mean field guess. We compute the density of states, we plot it, and we also plot the magnetization. And we do it again, but now with an antiferromagnetic guess. So we solve again the initial Hamiltonian with the same interaction, but now with an antiferromagnetic initialization. We compute the density of states, we plot it, and we also compute the magnetization, and we see the result. So if we look at the solution with a ferromagnetic guess, our final obtained self-consistent solution is a ferromagnetic state. So it's a state that has spins pointing in the same direction in all the sides. And it has a density of states that it's different from a one-dimensional chain due to the interactions. Now, if we look at the antiferromagnetic solution, what we have is a magnetization profile that it's indeed ferromagnetic. So it's positive here and negative in the next one. And now the density of states is very different. So we have a very large gap. So the first difference that we see here is that in a ferromagnetic state, we may have a metal, whereas in the antiferromagnetic state, we may have an insulator. And of course, the first question is that the true ground state of the system is unique. The system either is a metal or it is an insulator. So which one has the lowest energy? And this is precisely the first question that it is asked here. The answer is very simple. So if you look at the density of states, you can think that the average energy of the system is just the average value of the energy that you obtain from taking the density of states as a probability distribution for the energy, meaning that in this case, the average energy is going to fall roughly around here. So let's say around -1 approximately, whereas in this case, the average energy of the occupied states that are the states below 0 is going to fall at -3. So in general, if you have a certain self-consistent solution that opens up a gap, that usually will lead to a lower total energy, and that in turn will convert that state into the actual ground state. So in our case, the antiferromagnetic state is the ground state of the system. And now the next question is to compute the self-consistent solution for stronger values of the interaction and see what happens. Okay, so the interaction that we have here is 6. Now we can try to compute this with u equal to 10 and see how the solution looks like. And we can actually even increase the range of the energy so that we see everything. So let's create here an array for the energies. And we add it here in the density of states, and we also add it over here in the density of states. So now we can see everything. So you see that with interaction equal to 10, okay, we get a situation that it's relatively similar to the one before. We can now try to go to even stronger interactions. And when we go to u equal to 20, what you actually see is that now both the ferromagnetic and the ferromagnetic configuration look more similar than before. The actual difference is that the antiferromagnetic configuration still has a slightly lower energy than the ferromagnetic one, but now the energy differences are much, much smaller. So you can think that the average here is around -10, and the average here is also almost around -10, but this one turns out to be a bit smaller than this one, and this will become important later on in the lecture about magnetism. And one point to bring up is that, of course, in this limit of very large U, both the ferromagnetic configuration and the antiferromagnetic configuration are insulating in contrast with the intermediate U regime. Okay, now let us move on to another case that maybe it allows us to understand a bit better how the impact of electronic interactions is in an electronic structure. So we are going to look at a Hubbard timer. So instead of a chain, we are just going to consider two sites that have a hopping and that they have a certain on-site interaction between them. And we solve this problem using self-consistent mean field. So what we do is we take a chain with two sites per unit cell, we make it zero-dimensional, so we have just two sides, and now we are going to compute the self-consistent solution for different values of the interaction. So in particular, we are going to loop over interactions going from 0 to 10, compute the mean field solution, starting with an antiferromagnetic guess, and compute what is the expectation value of the magnetization. So this is going to tell us what is the magnetization that we get if we have interactions of a certain strength in the system. And then at the same time, we are going to compute the gap. We do this for the different hues, we plot it, and we obtain these plots over here. So let us look at this plot. So at u equal to 0, we effectively have just the bonding and anti-bonding state. So this gap is the bonding and anti-bonding gap. And then at very, very large u, we could even forget that we have a hopping and everything is dominated by the u. So in this limit, effectively all the gap is a correlated gap. It's just the energy that you need to give to the system to have more than one electron per site. And now if you look at the magnetization, you see something interesting. So at u equal to 0, there's no magnetization because the system is effectively single particle and non-interacting. And at very, very large u, you effectively have a quantized magnetization per site. So u equal to 0 is what we call the non-interacting limit. U equal to infinite is what we call the strongly interacting limit. So the limit in which we have one electron per site and this electron cannot fluctuate. And then in the middle, we see that there's a critical value of U, in particular 2, at which we start developing magnetization. Okay, so let us go through the question. So what is the non-interacting, strong interacting limits? Well, this we already discussed before. U equal to 0 is non-interacting. U equal to 10 is the strongly interacting limit. The magnetization saturates to 1 at large U because at very large U, we effectively get a single electron that is spin polarized per site, which corresponds to a set equal to 1 in units of the Bohr magneton. Then why is there a critical value to have a magnetization? Well, the reason for that is because the interaction needs to overcome the bonding and anti-bonding hopping. So as long as the interaction is weaker than the bonding and anti-bonding hopping, then our gap is going to be just a single particle bonding and anti-bonding gap, And then when the interaction is large enough, then we get our correlated gap. Why is there a gap even when there's no magnetization? Well, this is just our bonding and anti-bonding gap that we saw at the beginning of the session. This is the gap that just comes from the hopping of the system. And now the last question is, make the system bigger, what happens and why? And for that, let us just recall that for this system with two sides, we get this critical value at u equal to 2. So now let's make the system a little bit bigger. So let's take L equal to 2 and see which result we get. So at L equal to 2, you see that the transition is no longer at 2, but a little bit lower, right? And the same happens with the gap. Let's try to go even a little bit further. So L equal to 4. So at L equal to 4, you see that the transition moves a little bit to the left. And let's try, for example, L equal to 20. And you will see that at L equal to 20, our transition is going to move even a little bit further. So as you make the system bigger and bigger and bigger, then interactions are going to do something sooner. So you will need a weaker interaction in order to develop a correlated state. And this is in a way very much related with the evolution of the density of states as a function of the system size that we saw before. Okay, so now let's move on to the next case, which is the gap opening in the Hubbard model in a chain. This is also a more advanced exercise. So what we are going to do here is we are going to take a chain with two sides per unit cell. We compute the Hamiltonian, and then we solve this mean field Hamiltonian for different values of the interaction. And the values of the interaction range from 0 to 4. So every time that we solve the mean field Hamiltonian, we compute the electronic structure, in particular the band structure, and we compute the density of states. And what we are going to do is we are going to plot both as a function of the interaction. So we want to see how the density of states in a chain evolves as we go from the non-interacting limit to the strongly interacting limit. And the result of this is what you see in these two plots over here. So they effectively show the same information. It's just that the one on the left shows the eigenvalues and the one on the right shows the density of states. And so what you see is that at zero interaction, you have a continuum of states that is the same as you see as the red curve over here. And then as you increase the value of the interaction, you start opening up a gap that at very large values of the interaction becomes simply linear with the Hubbard interaction U. Okay, so the first question is, how is this specific converged mean field solution written mathematically? And the whole trick here is that here we are using a mean field Hubbard model with an antiferromagnetic interaction. And this antiferromagnetic interaction, this antiferromagnetic configuration is effectively the low energy configuration as we discussed before, and it effectively consists on having different exchange couplings in one side and in the other side. So if you label the sides of a one-dimensional chain with numbers like 1, 2, 3, 4, 5, even sides have positive magnetization, odd sides have negative magnetization, and this term enters in the Hamiltonian as a local Simon field, which is called a local exchange field after you do a mean field calculation. And now what this exercise asks us is to use a ferromagnetic initialization instead of an antiferromagnetic one and say what happens. So what we can do is just to replace ferro by antiferro here so that we use a ferromagnetic initialization. And when we do this, we obtain the following. So we see that the electronic structure also changes a little bit with the interaction, but now the system remains gapless all the time. And so what this is telling us again is that this ferromagnetic initialization is going to have more energy than the antiferromagnetic one, and this is not going to be the ground state of your system. Okay, good. So now let's move on to the gap opening in the Hubbard model, but now in the honeycomb lattice. So something that one could see in the linear chain is that it seemed as if the gap was opening right from the beginning. So once you start making you finite, then you get a gap. We will see that in the honeycomb lattice is slightly different. So we are now going to study a two-dimensional system instead of a one-dimensional one. The only difference is that we are going to change the geometry. So now we are going to use a two-dimensional honeycomb lattice. we are going to generate the Hamiltonian, and we are going to look at the spectra and the density of states as a function of the Hubbard interaction. So we solve the mean field equations at a certain u with an anti-ferromagnetic initialization. We compute the band structure, we compute the density of states, and we plot everything. And if we do that, we effectively obtain something like this. And the very interesting thing here is that now you get a gap opening, not for very small u's, but there's actually a critical value of u that you need in order to open this gap. And so what this is telling you is that in this system, there's a metal insulator transition as a function of the interaction. You may have a finite interaction in your system, but this finite interaction is not able to change the ground state of the system. So if you are at interaction 1, for example, that would be over here, you are not creating an insulator, and only when your interaction becomes large enough, then you are able to create an insulator. Okay, so then let's go with the quiz. So what is the difference that you see with respect to the linear chain? So the key difference is that in this system, there's a critical value, as we discussed before. Then next question is, at which interaction value do we get the symmetry breaking? Well, the value at which we get the symmetry breaking is the value at which we get a gap opening, which if you look at this plot, for example, this would be around 2.3, which is the critical value for the Hubbard transition in the honeycomb lattice with mean field. And then the next question is to replace the honeycomb lattice with a square lattice and what it's different. Okay, and this we can do just by going back to the code and just replacing the honeycomb lattice by a square lattice and running the calculation again and see what we get. And we will see that there's a huge difference between the honeycomb lattice and the square lattice. So these calculations take a bit, so let us just wait until they finish. And here's the result. So you see that in the square lattice, we actually get that the gap opens right from the very beginning. So this is very similar to the one-dimensional chain. So the difference is that in the honeycomb lattice, the density of states is actually fairly low. The density of states at the Fermi energy is actually 0 because you had this Dirac. But in the square lattice, the density of states at the Fermi energy is actually very, very large. You see that there's actually a peak here in the density of states at 0 energy. And what this actually means is that with an arbitrarily small interaction, you can actually create an opening in your electronic structure. And this is precisely what happens in the square lattice. And so in the square lattice, actually the critical value to get a correlated state is 0. So you get a correlated state with an arbitrarily small value of the interaction. Okay, let's move on with the next question, which is about symmetry breaking now with spinless fermions. So far we were focusing on Hubbard models, and the Hubbard model requires that your electrons have a spin degree of freedom, that you have spin up and spin down. One can have also correlated states without spin. For example, if you consider a system that is originally ferromagnetic and only up electrons appear at your Fermi energy, and you want to ask yourself, well, what is the correlated state that appears in this spin polarized electron gas? So this is what we are going to do now. So we are going to look at a one-dimensional system that does not have spin, and we are going to add a little bit of sublattice imbalance. And so the whole idea is that we are going to add a different type of interaction, which is, instead of Hubbard interaction, is going to be nearest neighbor interaction. So we're going to add a term to the Hamiltonian that is density in site n times density in site n plus 1. And this is a parameter that it's called V1. And so we are going to loop over different values of V1. We are going to go from V1 equal to 0 to V1 equal to 10. So we solve the mean field Hamiltonian at different values of the interaction, and we compute the expectation value of the density. And we plot this as a function, not of the density, but actually we take the density and we take the difference between the densities in the first site and the second site. So this is going to tell us what is the charge imbalance. So what is the difference between the charges in even sites and odd sites? And the plot that we get is the following. So at zero interaction, there's the same charge in the even sites and in the odd sites as it should be. But then as we increase the value of the interaction, we effectively get more and more charge imbalance between even sites and odd sites. Okay, so now let us go to the question. So why does the charge imbalance saturate to 1 for large interactions? Well, the reason is because the most extreme case is that we have 100% of the electrons in even sites and 0% of the electrons in odd sites. So in that limit, we would effectively have a charge imbalance of 1, meaning that we have 1 electron in the even sites, or in every single even site, and then 0 electrons in the odd site. And this, of course, working at half filling of the lattice. And now the next question is, what happens if we add some charge density wave externally to the system? Meaning, what happens if, even before including interactions, we add a different on-site energy in even sites and odd sites. So in a way, we help the system to go to a charge ordered state. And so this we can do just by adding this sublattice imbalance. So by default, it was 0. We can see what happens if we add 0.3. And so in that case, you will see that for 0 interaction, there's already an imbalance between the sites. And then as we make the interaction stronger and stronger, then this imbalance becomes stronger and stronger. And so in practice, if we have an external perturbation that promotes a symmetry broken state, then the symmetry broken state can become stronger from the beginning. And you can think that a simple analogy to this is the following. If you take a material that is magnetic and you apply an external magnetic field, you are in a way helping the magnetism to develop. In those cases, usually the energy scale of the magnetic field is much weaker than the energy scale of the intrinsic magnetization. So how much you are helping the system is hard to see, but in the case of charge density waves, for example, this is fairly easy to see. Okay, so let's move on to the next question, which is the gap opening in a spinless interacting model. So we are going to continue with the model that we were dealing before, so a one-dimensional chain with no spin and first neighbor interactions. And what we are going to do is we are going to see how the electronic structure and the density of states evolve with the interaction. So we loop over different values of the interaction. We perform a mean field calculation with nearest neighbor repulsion with a charge density wave mean field ansatz. We compute the electronic structure, we compute the density of states, and we plot everything. And if we do this, we get the following. So the states show that as you make the interaction stronger, a gap opens up, and at very large values of the interaction, your gap evolves linearly with the strength of the interaction. And then the density of states show that as you make the interaction stronger, indeed a gap is opening up. So the behavior that you see in the plot on the right is the same as the behavior that you see in the plot on the left. So now let us go with the question. So why does the gap increase with the interaction strength? Well, the reason is that the stronger the interaction, the stronger the sublattice imbalance that the interaction is inducing, and this sublattice imbalance effectively opens up a gap in the system. So the gap that you see here is an interaction-driven gap, and it's an interaction-driven gap that it's a charge density wave. And so now the next question is, well, what happens if we add a little bit of external charge density wave to the system, very much as what we did before. So we can do it again here. So instead of taking a charge density wave of 0, we can take a charge density wave of 0.3. We perform the whole calculation again, and what we observe is that already at interaction 0, we have a finite gap. And then as we increase the interaction, the gap becomes bigger and bigger and bigger. So again, having a little bit of sublattice imbalance at the beginning helps interactions develop a bigger sublattice imbalance. And so another way in which you can think about this is that if you have a system that has originally a gap that comes from some explicit symmetry breaking, that it's even external, then interactions can enhance that gap that you have here. And so in this case, you can think that you have an extrinsic symmetry breaking in this system, that is this external charge density wave that you are adding to the system, and then interactions make the system even more insulating. And so this is everything for today. Thank you so much for joining.